Welcome back to Statistics DSRT 734 course. In this lectures, we're going to discuss about hypothesis testing with two samples. Again, we have done hypothesis testing with one sample. We did it with regression. We did it with correlations, and also we did it with t-distribution, and also the z-score, which is the standard normal table. This time we are moving to do hypothesis testing using, again, two samples. There are two types. Our first lecture will focus on large independent samples. And the second one will focus on the second lectures will focus on the small independent samples. So again, this lecture is testing the difference between means, large independent samples, at least two different samples, two independent samples. So our main objective is to learn how to determine whether two samples are independent or dependent, and also learn how to perform two sample z-tests for the difference between two means. And this is the population mean, mu1 and mu2, using, again, large independent sample. In our next lectures, we're going to discuss about using small independent samples. So again, in our previous lectures on hypothesis testing, we were able to test population mean, but using only one sample. This time we are going to use two samples. We're going to determine if the two samples are dependent, that means they depend on each other. If one value changes, the other sample value will change, or if, again, they are independent. So this is, again, two sample hypothesis testing. Here we are going to compare two parameters from two populations. So our parameter here is, again, the mean, two population mean. So we are going to use the sampling method. That's independent samples. Independent sample means the sample selected from one population is not, again, related to the sample selected from second population. So again, the samples are independent, which means if I have two or more samples, they are not related to each other. So here we say the sample selected from one population is not related to the sample selected from a second population or other population. This means they are independent samples. Now, dependent samples can be paired or matched samples. Here we say that each member of one sample corresponds to the member of the other sample. So here we can see that, for example, if we have two dependent samples, it means they are related. It can be either paired together or matched samples. So each member of one sample corresponds to a member of other sample. So again, the two samples are related. So that's the difference between the two independent samples and dependent samples. Independent samples means the members of the samples are not related. They don't depend on each other. Dependent samples mean the members of the samples are related. So here we have independent samples, sample one, sample two. We can see that here even you can see the sample two is more than sample one. In sample one, we have 4 items. Sample two, we have 7 items. They are not related, they are independent. But in dependent samples, we can see that both sample sizes are the same and each member is related to each other. So this is, again, dependent sample. Each member of the sample of one are related to each member of sample two. So we can see the size also are the same. Independent samples, it doesn't matter. They are not related. The sample size doesn't matter. So we have an example here. What's the difference between independent and dependent samples? So we're going to classify the pair of samples, whether they are independent or dependent sample. Now, sample one says resting heart rates of 35 individuals before drinking coffee. The resting heart rates of 35 individuals before drinking coffee. Sample 2, resting heart rate of the same individuals after drinking 2 cups of coffee. So which means sample 2 size will be the same 35, because they say resting heart rates of the same individuals after drinking 2 cups of coffee. The resting heart rate of 35 individuals before drinking coffee, after drinking coffee. So we have 2 samples now. These samples, solution will be dependent samples. They are related because they are the same members. The first sample is resting heart rate. We measure their resting heart rate of 35 individuals before drinking coffee. The second is what? The same resting heart rate of the same individual, So they are related, the same after drinking 2 cups of coffee. So the solution will be, this is a dependent sample. The samples can be paired with respect to each individual. Because again, we have sample 1, sample 2. The same members are in both samples. The only condition changes here that in sample 1, their resting heart rate was taken before drinking coffee. Now in sample 2, the same individual resting heart rate were taken after they drank 2 cups of coffee. So next, they say we should classify again the pair of samples as independent or dependent. We saw the first example, they are dependent because we can see that sample 1 and sample 2 is the same individuals, 35. Now in sample 1, in this example 2, the test score of 35 statistics students. Sample 2, the test score for 42 biology students who do not study statistics. So they are not related. We can see, actually, they even stated here for us. The test score for 35 statistics students. But the second sample is 42 biology students. Maybe these biology students, some of them took the test for statistics, so they can be related. But here it was stated to us, test score 42 biology students who do not study statistics. So they didn't take test for statistics. So this will be independent sample. It's not possible to form a pairing between members of the samples. First of all, even the sample size are different, 35 and 42. The sample size are different. And second, the data represents scores for different individuals. In order to be able to say they are dependent, first, the sample size have to be the same. And we saw the diagram. Okay, so we move to the next step of our lectures. The first part, we know the difference between independent and dependent variable. Now, this is the main part of our lectures, how we can test 2 samples with independent samples. So here we have 2 sample hypothesis tests with independent samples. So the steps are the same. First, we're going to state our HO, the null hypothesis. So here we have a start hypothesis that usually states there is no difference between the parameters of the 2 populations. There is no difference between the parameters of 2 populations to state the HO. Then example here always contain the symbol less than or equal, or greater than or equal. Then we have our alternative hypothesis, HA. This will be the start hypothesis that is true when HO is false. So HO tells us there's no difference between the parameters of the 2 populations. Again, remember here we are doing 2 sample hypotheses. So we have 2 different populations. So a statistical hypothesis that usually states there's no difference between the parameters of 2 populations. Now, alternative hypothesis will always go against HO. So a start hypothesis that is true when HO is false. Then also it always contains greater than, not equal, or less than. If we have less than or equal, then it will be greater than. If it's equal, then not equal. If HO is greater than or equal, then it will be less than. So these are the possible HO and HA. So if HO, we say that the first population, the mean mu1 is equal to mu2, then HA will be what? Against it. So mu1 not equal to mu2. Now, if HO said mu1 is less than or equal to mu2, then HO will be mu1 is better than mu2. If HO said mu1 is greater than or equal to mu2, then HA should be mu1 is less than mu2. So we can see that HA is true when HO is false. So here we say, regardless of which hypothesis you use, you always assume there's no difference between the population means, or mu1 is equal to mu2. Now we're going to do our 3 conditions that are necessary to perform the Z-test. Remember, when we're doing one sample test, first we state our HO and HA. Then the next step, we do what? We find our Z-score. Then the next step, we use the standard normal table to get our p-value. Then we compare the p-value with the alpha value, which is the level of significance. Now, either we accept or reject HO. It depends on the p-value. The same steps here, only that here we are testing 2 samples or 2 populations. First step, we state the HO and HA. Second step, we need our Z-test now. So here we say these are the 3 conditions that are necessary to perform a Z-test for the difference between the 2 population means. So we can see it's the same step. State HO and HA, now we're getting our Z. But here, since we are testing 2 populations, a little bit different from when we are testing only 1 population. So first, we have to get the samples must be randomly selected. That's the first condition. Secondly, also the samples must be independent. Actually, this test we say 2 independent sample testing, hypothesis testing. So our sample have to be independent. Then thirdly, each sample size must be at least 30. This is what we mean by large sample. Small sample means if the sample size is less than 30. And we're going to do that in our next lectures. So here we say each sample size must be at least 30 or more, or if not, each population must have a normal distribution with a known standard deviation. So again, these are the conditions. The first thing we did, again, let me go back, is to state our HO and HA. After we state our HO and HA, the next step is finding the Z-test. So our Z-test, these are the conditions. Remember, we have 2 populations here. So first we say the samples must be randomly selected. Secondly, the sample must be independent. Then thirdly, we are doing a large sample. So the sample size must be at least 30 or more. Then if these requirements are met, then we can do our sample distribution for the difference of the sample means. That is the first sample mean minus the second sample mean, which is S1 bar minus S2 bar. This will be the difference of the sample means in a normal distribution. With the mean will be mu x1 bar minus mu s2 bar, or mu1 minus mu2. Now, there's a little bit difference here. We know the standard error in our, when we are doing only 1 sample testing, the standard error will be the population standard deviation divided by square root of the sample size. Now here we have 2 populations now. So the standard error, which will be the sigma x bar 1 minus s2 bar, because we have to get 2 samples to population, it will be square root of sigma square S1 bar plus sigma square S2 bar. And this is the same as writing the variance, because sigma square is the variance, 1 divided by sample 1 plus the variance of the second population divided by, again, the sample size of the second sample. So this is a new formula we are seeing here to find the standard error, again, for the one sample testing or testing one population. Is only the population standard deviation divided by square root of the sample size. Here we have two populations we are testing, or two samples. So it's the first one, variance for the first population divided by the sample, the first sample, plus variance of the second population divided by the sample of the second sample size. Everything square root. So after we find the standard error, then we can do our sample distribution for the difference of S bar 1 and S bar 2. And we can see from the diagram normal distribution here. And the mu1 minus mu2 will be the center, the difference of the two. Then to the right, we have the S bar 1 minus S bar 2 to positive. Then to the left will be negative S1 bar minus S2 bar. Remember the normal distribution, the center of this is Z. The center of the Z will be 0. To the left will be negative Z value, to the right positive Z value. Again, we're going to do an example in few minutes. So next, the test statistics will be, again, as we said, the difference of the first sample mean and the second sample mean. So the standardized test statistics, again, a new formula here. We said the Z will be the difference of the sample mean, first sample mean, and the second sample mean, minus the difference of the population mean, first population mean, and second population, divided by standard deviation. Then where the standard deviation of S bar 1 minus S bar 2 is what we previously, the formula we went through. So this is called a standard error. So it's like the Z will give us, in a previous, if it's only one sample, remember it was X bar minus mu over the standard error. Now it's the same thing, but here we have two samples, two population. So difference of the two samples minus the difference of the two population over the standard error. But this time the standard error formula is here. This is different. In a one sample size with a Z, the standard error will just be the population standard deviation over square root of the sample size. Here to be the population variance over the sample size for first data, then the second data or the second population variance over the second sample. And that will give us the standard error. Now, when we get the Z value, we can now test for our P. So here we said that when the samples are large, you can use S1, S2 in place of, again, sigma 1 and sigma 2, which means we can use the sample standard deviation instead of the population standard deviation. Now, if the samples are not large, you can still use two sample Z-tests, provided that the population are normally distributed, if the population is normally distributed, and also the population standard deviation are known. So let's put these steps all in words and also in symbols. So we know hypothesis testing, the first thing we do, we state our HO and HA. Second, we identify our significance level, the same step as the previous hypothesis testing using only one population. Here we are using two population or two samples, but we still have to identify our alpha value. Then we sketch our sampling distribution, which will look like a normal. Then we determine the critical value Here we are doing the Z, so we're going to use the standard normal table. So use table 4 means the standard normal table for we doing the Z test. Then if we know the p-value, after we get the Z and we get the p-value, then we can determine our rejection regions based on the p-value and also the alpha. We already identified the alpha value. Now to find the standardized test statistics, this is the formula for the Z. Then from this value, we can look for the p-value. Then when we get the p-value, we can determine the rejection or accepted region. Then we interpret our decision in the context of original claim. So now this example will help us go through what we just learned today, and this is our main objective. Again, the first part, we learn the difference between dependent and independent samples. This is the main topic. We are learning here how we can test two populations if they are two population mean if they are the same or they are different. And we saw the steps. Now let's look our example here. Here they say a consumer education organization claims that there's a difference. See, they claim that there's a difference in the mean credit card debt of males and female. So this means we have two different populations, the male population and female population. The result of the random survey of 200 individuals from each group are shown below. The two samples are independent. Well, here they already create for us, they are independent. Do the results support the organization claim? Use alpha 0.05 as our significance level. So here we can see that we have two populations. We have the females and also we have the males. And this is the data given to us. The female, the sample mean, the amount is 2,290. For male, the sample mean was 2,370. Now, the standard deviation for the first sample, which is the female, is 750. The standard deviation for the male is 800. Now, this is, in fact, this sample is independent, but still the sample size are the same, 200 and 200. So our goal is that we want to test the claim. The claim here said that the Consumer Education Organization claims that there's no difference in the mean credit card debt of males and female. So we have a sample of male and female. We know the average credit for male and the average credit for female, the sample size for both of them, and also the standard deviation for the credits, both of them, we know it. So now we want to do our hypothesis test to test if the claim is true or false, whether we should accept it or reject. So the first thing we're going to do is to state our HO and HA. We can see from the question already, is there a difference? There's no difference because the question here said, the claim said the Consumer Education claims that there is a difference. That is the claim, there's a difference. So the HO means there's no difference. HA means there's difference. That's the claim. So we have HA, the mean 1 not equal to mean 2. Also, the alpha is given to us to be 5% or 0.05. And remember, we have the 200 was given to us for both the male and female sample size. So this is the data we have. The next thing, we can draw our rejection area. Remember, we are using, actually that's why the slides didn't show us here. We are using the same formula for the Z1 minus alpha over 2. Now, since alpha is 0.05, we divide it is this way. We are doing two-way here. We say the claim is not equal, HO is equal. So this means we divide the alpha 0.05 by 2. So we get 0.025 to the left, 0.025 to the right. If you're going to look for the Z value, Z1 minus alpha over 2, you will get a Z value to be 1.96, the positive side, then the negative side will be negative 1.96. Again, the step didn't show here the reason why we did this already. So if you forget this, go through the hypothesis testing for one sample or one population using the Z. The steps are there. Okay, so the next thing, the formula changes. When we say it's only one sample, remember the Z was X bar minus the population mean over standard error. The same formula here. So here, what is the difference between the sample mean of both? We have 2290 and 2370. Also the difference of the sample size. The sample size are the same, so it's 0. 200 minus 200 is 0. Then remember we have the variance. The variance over N1, the sample size 1. The second variance over the sample size 2. But again, both of them sample are the same. So we use 200. Then we have the variance. And actually in the question, they give us the standard deviation. So that's why we square it to get the variance. So when we do all this calculation finish, we get negative 1.03. Again, we saw the formula here in our previous slides. The test statistics means the difference of the two samples. Here they give the first sample for female 2290, then 2370, the difference. The same thing we have to minus the difference of the two sample size. Here also the sample are the same, 200 minus 200, so it's 0. Divided by the standard error. The standard error for, again, two population testing or two sample testing, it will be the first variance of the sample or population divided by the sample size. The second variance of the second, that's the second population divided by the second sample size. So our result is given to us. So if we have negative 1.03, when we come here, remember our significant level was 0.05, which we divide into 2. So we get 0.025 to left, 0.025 to the right, because we're doing two-way. So we can see that here the negative 1.03 fall in the brown area. And this is called the accepted area. So our decision will be we fail to reject HO. We have to accept HO. Now, if this Z value falls in the blue area to the left or to the right, then we are going to say we're going to fail to accept. So here, the blue area is to reject area. The brown area is to accept. So our decision will be fail to reject HO. So we know the significant level was 5%. So we said at the 5% level of significance, there is not enough evidence to support the organization claim that there's a difference in the mean credit depth of males and females. Remember, the question, they claim that there's a difference between the male and female credit. But when we do that's why our HO said they are the same. And HA, the claim said they are not the same. But based on what we just did right now, the calculations, the significant level was 0.05. So the accepted area, blue, we divide into 2, 0.025 to the left, 0.025 to the right. So the brown area will be the accepted area. Then when it fell around the blue area, after the significant level, blue area, again, that will be the rejection. So this means the claim that they make that there's a difference is not, we fail to again reject HO. We accept HO that they are not, they are the same. They are the same. So that will be the summary of, again, doing hypothesis testing for two samples, 2 independent sample, and also the large 2 independent sample. When we say large, it means the sample size has to be 30 or more. So we saw the steps again. The first step, we have to state our HO and HA. The second step, we have to find our region. We have to do the z-test. First, we find that we know the alpha value. When we know the alpha value, we can come up with our region based on the alpha value. Like example, our alpha value was 0.05. So to the left will be 0.025, to the right 0.025. Then we have the critical zone, the accepted and rejection area. So when we know this in the graph, the next step is to find the Z. We saw that the Z formula is almost close to doing only one hypothesis testing. Normally it's the sample mean minus population mean over the standard deviation of the sample, which is the standard error. But here we have a different formula. The formula we have to use there is 2 samples. So the difference of the sample mean of the 2 samples minus the difference of the population, then divided by the standard error, which the standard error use the formula of square root. Then you have the population variance over the sample, the first sample. Then the second, we have a population variance again, plus the population variance over the second sample size. And that's the step. So if we get a Z value, again, we can go straight. This is what I'm trying to, so this is the whole thing we are doing. First step, we state our HA and HO. We know identify the alpha level, because identify the alpha level can give us the diagram for the accepted region and rejection region of HO. Since it's 0.05 and it's two-way, this is two-way, mu1 equal to mu2 and not equal. So we again have to, then we know the accepted and rejection region. Then from there, we already know sample size have to be given. So from there, we can find our test statistics. And we see the Z value fall within the blue area or the brown area. If it fall within the blue area, then we have to accept HO. I mean, the brown area where market size is, we have to accept HO. If it fall on the blue area outside, then we have to reject HO. So again, wish everybody the best. And we will see again in the second lectures on this. So the next lectures, which is the second lectures on testing 2 different populations, will be using the small, again, sample size, using a very small sample size, which means it will be less than 30. Again, thank you. Wish everybody the best.